Next, we will look at optical flow. So optical flow is an apparent motion in an image. So if you have 2 or 3 images of a particular thing that's happening in a scene, then optical flow can be used to identify what's moving or what objects are moving in a picture or a set of pictures. So when an object is in a video is moving, or sometimes when your camera is moving, then optical flow can be calculated to determine the apparent motion in an image. Now, optical flow determines two things. The first is the direction of the features of the direction of the things that are moving in the image, the features that are moving in the image, and the second is the speed of this motion. For example, if a car is moving in a video, then optical flow can be measured to calculate the direction of the car and the speed of the car, and usually optical flow is measured in pixels per second, and this is a vector quantity, so it gives you the direction as well and the scalar, that is the speed of movement as well. Optical flow that is measured in pixels per second encodes useful information about the scene structure. Now, here's an example. In a video of a scenery taken from a moving bus, let's say there's a bus moving and we can observe the scene through the window of the bus, then objects that are very far away, in this case, for example, if I was driving a bus through this street, then what you will notice is people that are closer to the bus or the scene that's closer to the bus will be moving faster, and scenes that are far away from the bus will be moving slower. So this apparent motion or optical flow of objects in the scene can tell us about what object is closer to the bus or what object is far away. Let's see. As you can see, as the bus driver is driving the bus, the objects that are very far away from the bus are moving less in the image, and the objects that are very close to the bus are moving very, very quickly. In other words, they have very high optical flow. So you can see that some of the trees that are very far away from the bus is not moving much in the picture, suggesting very low optical flow. Whereas even when the bus is moving, there are objects that are closer to the bus move very fast, suggesting higher optical flow. Now, one of the consequences of this is that as the bus is moving, if we know the optical flow of various objects in the scene, we can even calculate how far away the objects can be in the image or in the video. So optical flow can have further applications of calculating the speed or like calculating the distance between our source and the destination objects of interest as well. Now, I would like to ask you to find the differences between these two pictures, picture 1 and picture 2. What are the differences? So you may have quickly noticed that one big difference is that the bat that this player is playing in this picture is slightly higher than the position of the bat in this picture, right? So if you look carefully, you'll find more differences in these two pictures. So here are the differences in these two pictures. The overall scene in the second picture, as you can see, is slightly moved towards the right. That's because you see the gap between this wooden bar and the sort of the picture camera is bigger in this picture. Also, you can notice that the player's this particular leg is slightly off further on the left, and that's captured by this flow of the objects in the picture. So here we can say that the overall the player has slightly sort of like leaned down, and that's captured by this flow. So this captures the difference between the two pictures. Basically, this is the optical flow of the objects in picture 1 compared to picture 2. We also noticed that, say for example, the hill, this particular leg's hill has gone down, and that's captured by this tiny arrow over here. So looking at this input picture and just this, which basically is the optical flow in this picture, we can guess what the output picture may look like, right? Or we can, looking at these two pictures, this is the input, and let's say this is output picture, or the next frame of our, if it's a video, a next frame of picture, then we can calculate optical flow. So how can we represent optical flow? Basically formally, so that we have numbers that tell us like, what is the optical flow, and maybe come up with a graph like the one that we just saw, and so on. So how to represent optical flow? For any point xy in a given image, let's say in my current image, I take any position xy, any pixel xy, the optical flow can be described by Vx in the x direction and Vy in the y direction. So if my image has, let's say, one pixel, let's say for example I look at this particular pixel, and in this image, let's say the pixel has gone slightly down, assuming that my overall picture is in x and y frame. So here's my x-axis, here's my y-axis. Maybe this starts from 0 to 100 pixels, and let's say 0 to 100 pixels. Then in the next frame, so this is my first frame, and this is my I plus 1th frame. Then how far did this pixel move in the x direction, if it moved at all, and how far did it move in the y direction, is represented by Vx and Vy. And to measure the optical flow for each pixel or each point xy, we need to find the corresponding points between one time frame and the next. So if I know that here's my input pixel in this image, and if I find the corresponding input pixel in the next frame, then I can calculate Vx and Vy. So Vx gives me how far the pixel has moved in the x direction, and Vy gives me how far the pixel has moved in y direction. So here, this pixel is the xy in the current frame, and this pixel, same xy, is in the next frame. Then the immediate question is how to find such a corresponding points between one frame and the next. So right now I see that at this position, maybe say x equals 90 and say y equals 10, I have this pixel. How do I know where this pixel has moved in the next frame? How to calculate that? What computational technique or algorithm can I use to find out the location of the exact pixel in the next frame? Overall, the question is how to superimpose the current images xy and the next images xy. So how do I basically find out a block of pixels in this image that matches a block of pixels in the next image? Now let's try to answer this. That is, how to find the corresponding points between one time frame and the next time frame. The principle that we're going to use, the idea that we are going to use, is that image patches around corresponding points have similar intensity patterns. What this basically means is, if I have this bar, if I look at this block of pixels in this image, then no matter how much, like, if it has moved a little bit, no matter how much this picture has moved left or right, there will be a block of pixels in this image that sort of exactly match or is very similar to this block of pixels in the original input image. So this idea can be used to find most similar or matching patches, or these blocks of pixels, these matching patches. Let's start by taking an example. Say we consider a block of pixels centered at this pixel P. So say I'm looking at a block of pixels, and let's say this is the block I'm looking at. Here I'm enlarging it, and let's say the center of this pixel is P, and we're looking at this block, pixel block, the entire pixel block here. And let's say the coordinates of this center pixel P is x0 and y0, and this is at time frame t. Next, we choose some small values for dx and dy. So dx and dy are small values that we choose. Let's say, for example, we choose dx as 5 and dy as also 5. These are tiny values that we can experiment and sort of try, but these are smaller values that we can add to x naught and y naught, our current focus, our current pixel that we're looking at, position of that pixel. So what we do is, after we have chosen random values for dx and dy, we compare this block of pixels with many pixel blocks centered at various candidate pixels, x plus dx and y naught plus dy in the second frame. So once we have chosen this block, this particular block in our input, then what we do is we choose, so now we have chosen 5 and 5. So what we do is, and let's say this is my x-axis, here's my x-axis. Let's say this ranges from 0 to 100, and in y, this is my y-axis, also ranges from 0 to 100. Then I'm going to, and let's say this pixel, let's say for this pixel, x naught, y naught is, let's say 70, 15, right? So then what I do is add 5 to both. That means what I'm going to do is, in the second frame, I'm going to go to 75, slightly over here, 75 and 20, slightly above. So then I'm going to consider this block of pixels around that point. So now what I have is my input pixel block, input block of pixels centered around P, and I have another block of pixels in the next time frame, which is centered around x naught plus dx and y naught plus dy. Then what we do is calculate the sum of squared differences of intensities for these two blocks. So I take this block that I have, this is my input block, and then I take this candidate block, and then calculate sum of squared differences, SSD. This SSD is very easy to calculate. SSD for this dx and dy that we have chosen, currently we selected it as 5, 5, will be equal to for all the xy in my pixel blocks, that is for each pixel in my pixel block, what I'm going to do is calculate the difference of the intensity in the current pixel and the pixel in the next time frame, maybe the frame exactly that corresponds into the pixel that corresponds into the next frame, square it and then sum it over. So this gives me how similar or how different the block that we picked up in the second time frame is to our input pixel block. Now what we can do is repeat this process for various values of dx and dy. Usually we can choose dx to be something like from -10 to +10 and dy to be similar. So in other words, for an input image block, pixel block of my input image, if I look for many pixels around wherever it was, then it is very likely that I'm going to find a pixel block that has a very, very minimum SSD. And that very likely gives us how far this pixel x naught, y naught, our x naught and y naught, has moved in the second time frame. So how is optical flow calculated? How to calculate optical flow? Say that our input pixel of interest in our input image is x naught, y naught, and this is we're looking at a frame at time equals t. And what we would like to do is calculate the optical flow for x naught, y naught. And let's say that from the previous slide, we were able to calculate the optimal values of dx and dy that gives us the minimum SSD. So once we have that, what we now have is the number of pixels that this pixel has moved in the second time frame. So then x naught plus dx and y naught plus dy is the location of the pixel in the new time frame, obviously, right? Then we define optical flow at this location, at this pixel, for this pixel x naught, y naught as vx comma vy equals dx by dt comma dy by dt. Now it's very important to understand that this unit for optical flow is pixels per second. So if my time frame in the next picture, let's say, was 2 seconds, then my optical flow dx dy would be like, whatever value we get. Let's say if we get dx as 5 pixels and dy as also 5 pixels, then my optical flow will be 2.5 pixels per second, comma 2.5 pixels per second. In other words, time plays a very important role here to calculate optical flow. If this frame was a frame, let's say after 200 seconds, then of course our optical flow values must be different compared to what we have. So basically we are looking at the change in pixel per second or per unit of time.